Hello, in this video I'm going to cover the topic of mechanisms in organic chemistry. Now this is an area which over many years of teaching I've had lots of students, particularly as they revise for their exams, come and ask me about this topic as if they haven't quite got it first time around, and they really appreciate just a little bit of extra explanation, a bit of extra support. So I hope you find this useful. This video has been produced as a request from my IB class this year, so thank them if you find this useful. If you do find this useful, please do like, subscribe, share, and do leave a comment below if there's other videos that you'd like me to make to explain other tricky topics. So in this video I'm going to cover mechanisms, I'm going to cover the definitions and some of the conventions that we use when writing mechanisms for organic chemistry. I'm going to give you an overview of the mechanisms that I will cover in the rest of the video, and I will go through some further detail from each of those mechanisms. Now, I do teach AQA A Level and IB, and so if you do a different board and if I've not covered a mechanism that you need to know, then again, please do put a comment below and I'll cover that in a separate video or add it to this one. This is likely to be a fairly long video, and so I recommend you don't necessarily sit down and watch the whole thing in one go. I'll put in the description below some timestamps to help you to find the right bit of the video for you to go on to and have a look at. And so hopefully you'll find that helpful, and again, do let me know if there's other bits of information that you think would be helpful. Okay, so first of all, some definitions. Now, firstly, what is a mechanism? Well, a mechanism is a way of breaking down a chemical reaction, any chemical reaction, into a sequence of logical steps. You'll also meet the idea of mechanisms with the rate equation and talking about orders of reaction and the rate determining step. And within a mechanism, each step of the mechanism will have no more than two species, by which I mean molecules, particles, ions, that react together. And that's because the chances of getting a collision between more than two species at one time is statistically very, very unlikely. Now, in organic chemistry, the mechanisms that we look at have usually two parts of the name. The name gives you the type of reactive species that reacts with the organic molecule, and it also gives the type of reaction that occurs. So first of all, let's have a look at the names of the three different reactive species that react with the organic molecules. So the first one is called a free radical. Now, a free radical is defined as a reactive species which has an unpaired electron. So it has just one electron by itself, and that's usually drawn just with a little dot. Now, free radicals are very reactive species because atoms or molecules with an unpaired electron are very unstable, and so therefore will react quickly in order to pair up that electron. The second type of reactive species is called a nucleophile. Now, nucleo for nucleus and phile literally meaning lover. So a nucleophile is a substance which would be attracted to the nucleus of one of the atoms on the organic molecule, usually the carbon atom. Now, nucleophiles, because they're attracted to the nuclei, will be attracted to positive charge and therefore will have a negative charge or a partially negative charge, but will always have a lone pair of electrons. So all nucleophiles have a pair of electrons, a lone pair of electrons, and the definition actually of a nucleophile is an electron pair donor. And then the third type of reactive species is called an electrophile. And if a nucleophile is attracted to nuclei, the electrophile is attracted to electrons. And therefore, electrophiles will either have a positive charge or a partially positive charge. And electrophiles will be substances that are missing electrons, so they're electron deficient species. And they would be an electron pair acceptor. And so electrophiles will react with organic molecules by accepting a pair of electrons from the organic species. And then again, there are three types of reaction. The first type of reaction is a substitution reaction. Now, in a substitution reaction, the reactive species will take the place of an atom or a group of atoms on the organic molecule. And so something adds on to the molecule, something else is removed from the molecule. Addition reactions happen only if there is a double bond on the organic molecule. And in addition reactions, you have the reactive species will add either side of the double bond, and as is implied in the name, addition reactions have two reactive species which add together, join together to produce just one product. And then finally, the third type of reaction is elimination. Now, elimination is a little bit different because elimination doesn't usually have the name of the reactive species before the elimination name. And the elimination reaction is the opposite of an addition reaction. So during an elimination reaction, something will be removed from the organic molecule, usually from two carbon atoms which are adjacent to each other, and those bits come off, produce a double bond on the organic molecule and remove a smaller molecule, often water or HCl, something like that. Okay, and now let's talk about conventions, because in organic chemistry we generally don't just write our reactions as a sequence of steps within the mechanism, because the other thing that we show in organic mechanisms is the movement of electrons. And you could imagine that historically at a meeting of IUPAC, the organisation that comes up with all the conventions in chemistry, you could imagine them all sitting around and scratching their heads and thinking, well, how could we show the movement of electrons within a static piece of paper? And perhaps somebody said, oh, I know, great idea. Why don't we use an arrow to show where the electron starts and where the electron ends up? And everybody goes, oh, fantastic, excellent, great idea. And then somebody else says, oh, but hang on, we already use arrows in chemistry, and the arrow is what separates the reactants from the products in a chemical equation. And everybody goes, oh no. And then somebody said, why don't we make the arrow that represents the movement of electrons an arrow with a bend in it, and we'll call it a curly arrow. Bravo, excellent, let's do that. And I don't know whether that's what happened, but that's the convention that we use. We use these arrows with a bend in to represent the movement of electrons. Now, when we write curly arrows, there are two types of curly arrow. There's a curly arrow which we use most often, which has a full arrowhead. Now, the full arrowhead is used to represent the movement of a pair of electrons, two electrons. Just occasionally with free radicals, we will only show the movement of a single electron, just one electron. And when we show these with curly arrows, we only have a single arrowhead. Sometimes these are called harpoons or fishhook curly arrows. Now, the curly arrows, whichever type you draw, will always start where the electrons start. So they'll start either at a chemical bond, which is where there is a pair of electrons, or at a lone pair of electrons, which would be for a double-headed curly arrow, or at an unpaired electron, just a dot, if it's the movement of a single electron, and therefore a single-headed curly arrow. So the arrow always starts where the electrons start, and the arrow head points to where the electrons end up. And so electrons will either end up on an atom if you are producing a lone pair with the movement of two electrons, or if you are producing a free radical, if you're just showing the movement of one electron. Or the arrow will point to between two atoms or next to an atom if you are producing a bond between the two atoms. Now, quite often at this level, if you show the arrow pointing to an atom, if you're making a bond with that atom, you will not be penalised in the exam. But it's worth just remembering that the arrow points to where the electrons end up. And often when marking exam papers, one of the most common mistakes I see is when people put the arrow the wrong way round. And so perhaps they point to where the electrons start from where the electrons end up, which doesn't really make sense because arrows go from where they start to where it finishes. And so just remember that when you're writing these organic mechanisms. Okay, so now before we get into the detail of the mechanisms, I'm just going to give you a bit of an overview of the mechanisms that we're going to cover. And I'm going to link these together, hopefully in a relatively logical way. So I'm going to put up a flow chart here of the mechanisms that we're going to cover. So we'll start with alkanes. Alkanes, saturated hydrocarbons, generally pretty unreactive molecules, but they do one mechanism, and the mechanism that alkanes undergo is the free radical substitution. Now, this mechanism is one which is often not drawn with curly arrows and does come up in every syllabus. The only thing is that it's not unique to alkanes. Any organic molecule with a carbon-hydrogen bond could undergo free radical substitution. And let's face it, that's pretty much all organic molecules could undergo this reaction. So anyway, the first reaction is the alkanes free radical substitution, which generally we do with a halogen, and therefore we produce in the substitution reaction a halogenoalkane. Now, halogenoalkanes undergo two different types of reaction. They undergo a nucleophilic substitution, and the nucleophilic substitution reactions of halogenoalkanes will produce either alcohols, nitriles, or amines, depending on the nucleophile that's used. Now, for IB, you only need to know the reaction that produces alcohols. But A level, you'll need to know the other two. The other mechanism that halogenoalkanes can undergo is an elimination reaction which produces alkenes. Again, that reaction is not covered at IB, but is at A level. The alkenes can undergo a type of mechanism which is electrophilic addition. Now, there are two possible products from electrophilic addition depending on the electrophile. We can either go back to the halogenoalkanes, or we can go to the alcohols through the electrophilic addition. Now, from the alcohols, and again this is an A-level only mechanism, the alcohols can go back to alkenes by another elimination reaction, the reverse of the electrophilic addition. So with our products from halogenoalkanes, the alcohols, the nitriles and the amines, the alcohols and the amines both undergo a type of mechanism called nucleophilic addition elimination. And these reactions produce esters from alcohols or amides from amines. And the nucleophilic addition elimination reactions can also produce carboxylic acids or N-substituted amides. Now, those reactions, the organic reactant in those reactions is not actually an alcohol. It is the alcohol would be the nucleophile. It is an acyl chloride. So that's studied within the acyl chlorides functional group or class. Now, alcohols can be oxidized to aldehydes and ketones and then on to carboxylic acids. The aldehydes and ketones can undergo a mechanism which is called nucleophilic addition. And nucleophilic addition reactions of aldehydes and ketones can either go back to alcohols in a reduction type reaction or can produce nitriles, depending on the nucleophile that's used. And then finally, the last mechanism that we'll cover is the mechanism electrophilic substitution, and that mechanism is from aromatic compounds, so organic compounds which contain a benzene ring, and from the aromatic compound through electrophilic substitution you can either make a ketone or you can make a nitro compound which can then be reduced to an amine depending on the reaction. So what we'll do now is we'll get into the individual mechanisms, and as I said before, you might want to, rather than watching the video all the way through, you might want to just go to the description below and click onto the mechanism that you want to review. So free radical substitution is a mechanism which appears in every specification, both at A level and standard and higher level IB. Nominally it's put with the alkanes, although free radical substitution happens with any organic molecule which contains a carbon-hydrogen single bond other than in benzene, in aromatic compounds. Free radical substitution is a chain reaction, and this is the only mechanism where you don't necessarily need to use curly arrows, and in fact at A level you won't use curly arrows. IB there is a chance to, and I will show that in a few minutes. So the essential condition for free radical substitution is UV light. UV light provides the energy to break apart the halogen, and that takes place in the initiation step. So what happens with free radical substitution is we start with initiation, and initiation is where we provide the energy to break apart the halogen. So if we take, say, chlorine as an example, in the presence of UV light we are going to produce 2 chlorine radicals. Now the radicals, the free radicals, are shown with a dot that dot represents the unpaired electron. And this is an example of homolytic fission. Once we've produced our free radical, then that can react with the organic, and that will take place in two reactions which are both called propagation reactions. Now, in this example, I'm going to react chlorine with propane, and I'm going to produce as my product 2-chloropropane. And so in the first of my propagation steps, I'm going to react my chlorine radical with propane, and I'm going to say that one of these two hydrogens from the middle carbon is removed by the chlorine radical. Now, the chlorine radical is very reactive because it has an unpaired electron, and that makes it unstable. It will do whatever it can to pair up that electron. And if the chlorine radical is in the vicinity of a propane molecule, the first atom that the chlorine will see is a hydrogen atom. So the chlorine will remove one of the hydrogen atoms. And as I say, in this example, I'm going to remove one of the hydrogen atoms from the middle carbon. And so I'm going to produce a propyl radical with the free radical on that middle carbon, and I will also produce HCl. In my second propagation step, this free radical which I've produced is going to react with another chlorine molecule, a molecule which is has not been broken, and so I have the propyl radical reacts with chlorine, and that will produce my product, the 2-chloropropane, and will also produce a chlorine radical. Now, that chlorine radical is able to go back into the first part of this reaction and will react with another propane molecule. Now, eventually, once all the propanes are used up, then a chlorine radical could actually react with any of the other hydrogens around the propane. And so ultimately, you could substitute all 8 hydrogens and end up with octachloropropane. So you get a whole mix of products ultimately in this reaction. Now, the final step that we put into the free radical substitution reactions is a termination step. Now, in a termination step, you basically take 2 free radicals and you combine them, and that stops the reaction. It terminates the reaction. Now, it doesn't matter which 2 free radicals you choose, although I would recommend you don't combine 2 chlorine radicals, because if you do, you'll go back to Cl2 and the reaction could start all over again if there is still UV light around. And so therefore the termination reaction, the simplest thing to do would be to take a chlorine radical and the propyl radical and just combine them together to produce another 2-chloropropane product. And there is only one product there, the 2 radicals have combined. But equally, you could combine 2 of the propyl radicals, and this would just produce an organic product. It wouldn't be, or a hydrocarbon product, it wouldn't be a halogenoalkane. And if we did that, we would produce this molecule, squeeze all the hydrogens into this. Oh, sorry, that's just a hydrogen there, apologies. And that would be 2,3-dimethyl butane as our product. That's a hydrogen there, apologies, that's a bit messy. So, as I said, that reaction could keep going round and round until we end up substituting all of the hydrogens. Now, I've drawn this mechanism using displayed formulae because it's a little bit easier to see what's happening, especially in the propagation step, where we can see the first propagation step, where we see we've got the chlorine radical will only remove a hydrogen from the propane molecule, because it's the hydrogens around the outside of the propane that chlorine radical is going to collide with in order to form the bond. Although it would be possible just to write normal equations. So if we start with the initiation, that's where we'd have chlorine producing 2 chlorine radicals in the presence of UV light. Our first propagation step is where the chlorine radical will react with propane, and because we're producing the propyl radical on the second carbon, it would not be acceptable to just write C3H7 dot, because with a 3-carbon molecule, the radical could be on the number 1 or the number 2 carbon. And because in this example I've chosen to make 2-chloropropane as my product, the radical would have to be on the middle carbon. So we have to draw a linear formula for that. Our second propagation step is where we have our radical reacting with a chlorine molecule, and that will make CH3CHCl, CH3, the 2-chloropropane, plus the chlorine radical, and then finally termination. And in this case, I'll just produce 2-chloropropane again. So we have the propyl radical and the chlorine radical producing the product. As I said, this is a reaction which is very difficult to control. So often in an exam, it'll tell you the product that the mechanism is going to produce, and you have to construct the mechanism accordingly. Now, I did say that this mechanism could be shown using curly arrows, and this is where we use the so-called fishhook type curly arrow. So with the initiation step, the homolytic fission, we've got our chlorine molecule, and we've got the pair of electrons in that bond. Now, 1 electron from that pair of electrons is going to go to the carbon on the right, and so we use a single-headed curly arrow to show the movement of 1 electron to that carbon, and another single-headed curly arrow to show the movement of electrons, or an electron, to the other chlorine. And so we produce two chlorine radicals. In our propagation steps, the first propagation step is where the chlorine radical removes a hydrogen from the propane molecule, and so what's going to happen is we're going to make a bond between the chlorine and the hydrogen. So we have 1 electron moving from the chlorine radical, and we have one electron coming from the pair of electrons in the bond and going to between the hydrogen and the chlorine to join with that in order to make the hydrogen-chlorine bond. The other electron in that carbon-hydrogen bond is going to go from the bond and will move to the carbon atom in order to produce the free radical. And we've also produced HCl. In our second propagation step, we have our propyl radical encounters a chlorine molecule, and we make a bond between the radical on the carbon and one of the electrons from the chlorine-chlorine bond, and so those two electrons are going to end up between the carbon and the chlorine to make a bond. The other electron in the chlorine to chlorine bond is going to move to the other chlorine atom, and so we're going to end up producing our product and the chlorine radical. And as I said, those two steps can go round and round in circles. And then finally, a termination step. If we again produce our 2-chloropropane as our product, this is where we will take our propyl radical and a chlorine radical, and these two unpaired electrons are going to pair up to form a bond between the carbon and the chlorine. And we're going to produce our 2-chloropropane product. As I said, at A level you don't need to know the single-headed curly arrow convention. At IB you may come across it. It's unlikely you'd be asked to draw out the whole mechanism using the single-headed curly arrows, but this is a way of showing that you can use single-headed curly arrows in this mechanism. Okay, so nucleophilic substitution mechanisms happen with a number of different organic functional groups, but they're focused on within the halogenoalkanes section for both A level and IB. Now, with A level, there are 3 different nucleophiles that you need to know, so I will go through all of those. IB just does one of those, but then goes into that one in a bit more detail. So I'll link to another section of the video where I go through that additional detail. So with the halogenoalkanes, the nucleophiles that we need to know are the with the hydroxide ion, for instance from sodium hydroxide, with ammonia, and with the cyanide ion, for instance with potassium cyanide. So I'll look at the hydroxide ion first of all, and so if we take, say, 1-chloroethane, there is a slight dipole here where the chlorine is slightly negative, the carbon is slightly positive, and that's where the attraction will come for the negative charge and the lone pair of electrons on the hydroxide ion, and so there'll be an attack from the hydroxide ion to the carbon, and so that will make a bond between the hydroxide and the carbon like that, and that will cause the carbon-chlorine bond to break, and so we'll end up producing ethanol, and the chloride ion will be separated. And so that's the most straightforward nucleophilic substitution mechanism using aqueous sodium hydroxide. As we've seen, or as we'll see in the elimination mechanism, there is another reaction which hydroxide ions can do with halogenoalkanes if the conditions are slightly different. But with an aqueous hydroxide ion, then this nucleophilic substitution mechanism will predominate. Now, at this point, IB students might want to move on to look at the SN1 and SN2 section of the nucleophilic substitution. But for the A-level students, the other nucleophiles that we need to know about, so we've got the cyanide ion. So if we have, for instance, 2-bromobutane, then the cyanide ion, which has a negative charge and a lone pair of electrons on that carbon, will attack the carbon, form a bond between the carbon on the cyanide and the carbon on the halogenoalkane, causing the carbon-bromine bond to break and producing a nitrile plus the bromide ion. Now, the nitrile, this is butane nitrile with a methyl group on the number 2 carbon, so this would be 2-methyl butane nitrile. This, you may spot, has an asymmetric carbon atom, and so therefore could have optical isomers, and we'll look at that slightly separately within the SN1 and SN2 section, which isn't required at A-level, but just be aware that optical isomers could be formed from this reaction. And then the last substitution mechanism that you need to know about at A-level is with ammonia. So this time, if I just take chloromethane and we use ammonia as the nucleophile, the same thing will happen. Attack the lone pair on the nitrogen, forming a bond with the carbon, causing the carbon-chlorine bond to break. Now, the slight difference in this mechanism is that we now produce an ammonium ion intermediate plus the chloride ion. Now, this ammonium ion could exist by itself, but if we have an excess of ammonia, then ammonia, as well as behaving as a nucleophile, can behave as a base, and so can remove a proton from the ammonium ion, causing the electrons in the nitrogen-hydrogen bond to go back to the nitrogen and produce methylamine plus, ultimately, ammonium chloride as the products. Now, this can get really messy because the methylamine has a lone pair of electrons, and the amine then can behave as a nucleophile itself, and so this could then react with another chloromethane and can substitute then each of the hydrogens on the nitrogen until ultimately you end up with a tetramethyl ammonium ion. And so because of that further substitution that can occur, it's very difficult just to produce one product, a single product. One way that you can try to get as pure a product as possible would be to use an excess of the halogenoalkane, and so therefore once we've produced the amine, the reaction stops and there's no more halogenoalkane for a further substitution to occur. The difference if you're writing an equation for this reaction, for instance, if we were taking chloromethane reacting with ammonia, we would need to add 2 molecules of the ammonia, one to act as the nucleophile to produce the methylamine, and the other to act as the base to remove a proton and to produce the ammonium ion, which would then pair up with the chloride to produce the methylamine plus ammonium chloride. So there is just look out for, if the question does ask you to write an equation, to remember that you need 2 molecules of ammonia to react with 1 molecule of the halogenoalkane. So another aspect of the nucleophilic substitution mechanism which will be of interest to A-level students but very important for the IB students is that there are actually 2 different possible mechanisms that can occur. Now, if we take the reaction between 2-chloropropane and a hydroxide ion, then what can happen there, as I said, there are 2 possible mechanisms for this. Now, the first mechanism is what's known as an SN2 mechanism. SN standing for substitution nucleophilic, and then the 2 meaning bimolecular, meaning that there are 2 reacting species, so particles, molecules and ions, in the first step of the mechanism. And so what will happen here is that the hydroxide ion will come in and start to form a bond with the carbon. At the same time, the carbon-chlorine bond will break, and so we'll end up with an intermediate. Now, the intermediate, which won't hang around very long, is where we start to form the alcohol and start to lose the chlorine. And so this ion would have a negative charge, and both the OH and the Cl will be associated with that carbon. As one starts to join, the other starts to come off, and then the product of that reaction is propan-2-ol plus the chloride ion. So that's the SN2 mechanism. Now, the SN1 mechanism is where there's only one reactive species in the first step. And so in this mechanism, we'll take the same halogenoalkane, so the 2-chloropropane. What will happen in this mechanism is that the carbon-chlorine bond will break first, will produce an intermediate, which is a carbocation, and this will be a secondary carbocation, and then and that will have the chloride ion, and then the hydroxide ion will then very quickly come in, form a bond with the carbon, and form our same products. So both mechanisms are possible, so I'll just leave both of them there on the screen. Both mechanisms are possible, but there are factors that influence which mechanism is more likely. So first factor is the type of halogenoalkane. So if the halogenoalkane is a primary halogenoalkane, so that's where the halogen would be attached to the number 1 carbon, then primary halogenoalkanes tend to undergo the SN2 mechanism. Secondary halogenoalkanes could be either mechanism, so that's why I chose a secondary halogenoalkane here. And tertiary halogenoalkanes, where the carbon with the halogen would be attached to 3 other carbons, so this hydrogen here would be replaced with a methyl group, for instance. So in the tertiary halogenoalkane, then the SN1 mechanism tends to predominate. And that kind of makes sense, because if you've got lots of carbons around this carbon, it's very difficult for the hydroxide to actually get in and attack the carbon, and so it's much easier if the halogen has been removed first. So that's the type of halogen: primary SN2 predominantly, tertiary SN1 predominantly, and the secondary could be either. The second factor that affects the most likely mechanism is the identity of the halogen. Now, the stronger the carbon-halogen bond is, and that would be with the smaller halogens, well, they tend to undergo the SN2 mechanism. There tends to need to be the attraction between the hydroxide and the carbon, causing the carbon-halogen bond to weaken and then break. And so if you've got fluorine as the halogen, then that will tend to undergo SN2. The iodine halogen is the weakest carbon-halogen bond, and the carbon-iodine bond can break relatively easily, and so therefore forming the carbocation intermediate is straightforward. And so if the halogen is an iodine, then the SN1 mechanism predominates. And then the third factor that affects the mechanism is the type of solvent. So if you dissolve your halogenoalkane and the nucleophile in an organic, which is basically non-polar solvent, and the technical name for that is an aprotic solvent, well, that tends to favour the SN2 mechanism. If you have a more polar solvent for the reaction, and that's known as a protic solvent, and there might be some water in there as well as maybe some alcohol to dissolve the halogenoalkane, then that tends to favour the SN1 mechanism. And the reason for that is that the solvent can surround the carbocation intermediate and just stabilise that positive charge, which means it's going to hang around for a bit longer and wait for the hydroxide ion to come in and join. There is a link here with kinetics and rate equations. So the SN2 mechanism, which is basically one step, would be first order with respect to both the halogenoalkane and the nucleophile, and so the mechanism would be second order, sorry, the rate equation would be second order overall. With the SN1 mechanism, this is a two-step mechanism, step 1 will be the slowest step in that mechanism. It'll be the rate determining step where we break off the halogen. Step 2 will happen very quickly as there's a strong attraction between the oppositely charged ions. And so the SN1 mechanism will be first order with respect to the halogenoalkane, but zero order with respect to the nucleophile, because the nucleophile appears after the slowest step, and so it'll be first order with respect to the halogenoalkane. Just a couple of ideas in terms of stereochemistry and optical isomers. So if we do an SN1 mechanism and have the potential to produce an asymmetric carbon atom, so for instance if our halogenoalkane was 2-bromobutane, if we react that with the hydroxide, then the SN1 mechanism tells us that the bromine will break off first, and we will end up producing a trigonal planar intermediate. Now with this trigonal planar intermediate, the hydroxide ion is equally likely to attack from above the plane of atoms or from below the plane of atoms, and therefore we could make two possible products where they have mirror images of each other, and the two mirror images of these will look like that, and so therefore you could get a racemic mixture being formed. Now if you do an SN2 mechanism with the same reaction, then what would happen if you had just one enantiomer? If you have just one enantiomer of your organic reactant, then what will tend to happen is that the hydroxide ion will tend to approach from the opposite side of the molecule to the polar bromine, and so the hydroxide ion will tend to attack from this side, causing the carbon-bromine bond to break. And then what happens is you get an inversion of the structure around that carbon. And so the OH would then be joined from underneath the carbon, the bromide ion would come off, and you get an effect that's similar to an umbrella blowing inside out on a windy day. And so as the bromine comes off, as the hydroxide attacks from underneath, these three parts of the molecule will flip up and will be now above that carbon atom, and so you get an inversion of the stereochemistry around that chiral centre. So the elimination mechanism, which doesn't come up at IB, so it's just for the A-level students, there are two different elimination mechanisms that you need to know. The first is with the halogenoalkanes and the second is with the alcohols. So I'll cover them both separately. So we'll start with the halogenoalkanes. So let's just take any halogenoalkane. Let's take 1-chloroethane. Now, normally, if you react 1-chloroethane with sodium hydroxide, you'll get a nucleophilic substitution reaction and end up producing the alcohol, the ethanol. However, if you change the conditions a little bit, if you dissolve the sodium hydroxide in an ethanolic solution, so have some alcohol in the solution as well, and if you heat this mixture under reflux, so continuously boiling with a vertical condenser placed into the flask, then you could also get an elimination reaction. Now, the elimination reaction happens when the hydroxide ion, instead of behaving as a nucleophile, behaves as a base, behaves as a proton acceptor. And if that hydroxide ion removes a proton from the carbon adjacent to the carbon with the halogen on it, then that will cause the hydrogen to break off. The electrons in the carbon-hydrogen bond will then form a double bond between the two carbons, and the chlorine atom will be removed as well in order to have the right number of bonds. And so therefore, in an elimination reaction, we will end up producing a double bond. So we will produce, in this case, ethene plus water plus the chloride ion. And so those are the products of this reaction. Now, it's worth noting that for this reaction to occur, there must be a hydrogen attached to the carbon adjacent to the carbon with the halogen. So if this carbon here had 3 other carbons attached, then there would be no possible elimination reaction. And that's something to watch out for in exams when there may be a question about that. Now, yes, this is an elimination reaction, but we do have that hydroxide ion, and so it would be possible to get some nucleophilic substitution taking place as well, and so therefore we would end up with a whole mix of possible products, one of which would be ethanol. The other reaction, the other elimination reaction that can happen is if we have an alcohol. And so let's take ethanol as an example. And this happens in the presence of acid. Now, an H plus ion would be attracted to one of the lone pairs of electrons on the oxygen, and so we could form a bond between the oxygen and the H plus ion, which would produce as an intermediate this ion with the positive charge on the oxygen there. Now, the next step in this mechanism is that the bond between the carbon and the oxygen will break, and so we'll remove water from the molecule. And as that breaks off, the hydrogen, one of the hydrogens from the carbon adjacent to the carbon with the oxygen, will break off and will form a double bond between the two carbons, and so will produce as a product the alkene, so ethene plus H plus from the carbon adjacent to the oxygen, and plus water. And so that's the mechanism there for the elimination of water from an alcohol. Now, in this example, we have H plus both as a reactant here and as a product over here. And so therefore, the acid, the H plus, is behaving as a catalyst for this reaction. So it's not used up by the reaction. Even though it is involved in the reaction, it's reformed, and the H plus here is a different hydrogen to the one that we started with. So the electrophilic addition mechanisms which occur with the alkene homologous series or class, if you're doing IB, and this is a reaction where an electrophile so that's a species which is electron deficient, has a positive or delta positive charge, is attracted to the electron density in the alkene and causes the double bond in the alkene to break, and then the electrophile adds either side of the double bond. So common electrophiles are hydrogen halide molecules where the hydrogen is slightly positive because the halogen is more electronegative, or a halogen, and we'll talk about that in a sec. And then the other one which at A level you need to know is sulfuric acid as an electrophile. So I'll go through those, and I'll go through the electrophilic addition to an asymmetric alkene as well as to a symmetric alkene. So first of all, let's look at an electrophilic addition reaction between ethene, so the most simple alkene, and notice that ethene has a trigonal planar geometry around the carbons. That's why we draw the hydrogens at an angle like that. Now, if ethene reacts with bromine, now bromine doesn't normally have a dipole moment because both bromine atoms have equal electronegativity. However, as the bromine molecule approaches the electron density in the double bond, that electron density repels the electrons within the bromine bond, and so therefore that repulsion induces a dipole on the bromine molecule. So the end of the bromine molecule, which is furthest from the electrons in the double bond, becomes slightly negative, and the bromine atom, which is closest to the electron density, becomes slightly positive. So we get an attack coming from the electrons in the double bond, forming a bond with the bromine atom. And so the electrons will end up between one of these carbons and that bromine. Bromine can only form one bond, so that causes the electrons in the bond between the bromine atoms to move from the bond to being just on that one bromine. So the bromine will then add to one side of that double bond. The other side of the double bond is now electron deficient. So of the two electrons in the double bond, both of those electrons are now between the carbon and the bromine. Therefore, the carbon on the other side of the bond loses an electron and so becomes positive. It becomes a cation, and because it's a cation on a carbon atom, that's known as a carbocation. And that's the intermediate. We have a carbocation intermediate. Now what will happen next is that the bromide ion, which was formed by breaking the bromine bond, will be very strongly attracted to that carbocation, and very quickly that bromide ion will form a bond with the carbon and will end up producing 1,2-dibromoethane. And so that's the electrophilic addition mechanism. Now, I mentioned before that sometimes the alkene may be asymmetric. That means that the double bond is not right in the middle of the molecule. And so an example of that could be propene. So if we have propene like this, again the molecule will be planar around the double bond. And if we react that with hydrogen bromide, that molecule has a dipole. Bromine is more electronegative than the hydrogen, and so therefore the bromine atom will be slightly negative, the hydrogen atom will be slightly positive, and there will be an attraction then between the partially positive hydrogen and the electron density in the double bond. And so we'll get an attack from the double bond making a bond with the hydrogen, causing the electrons in the HBr bond to form a lone pair of electrons on the bromine. Now, because this molecule is asymmetric, the hydrogen could attach to either of those two carbons, and so therefore there are two possible intermediates to this reaction. So if the hydrogen attaches to the number 1 carbon, the carbocation will be on the middle carbon, and so that is known as a secondary carbocation. And again, in that case, the bromide ion will be very strongly attracted to the carbocation, will make a bond with the carbon, and will end up producing 2-bromopropane. Now, if the hydrogen atom attaches to the second carbon of the chain, what we will produce here is a carbocation on the number 1 carbon, and the hydrogen is attached to the number 2 carbon. And then the bromide ion, again, the curly arrow will come from the lone pair of electrons on the ion, forming a bond with the carbocation, and will produce, in this case, 1-bromopropane. And both of those products are possible. However, one of those products is formed in greater quantities than the other. And the product that's formed in greater quantities is the 2-bromopropane. And the reason for that is due to the stability of the carbocation intermediate. And the secondary carbocation, it's secondary because the positive charge is on a carbon attached to 2 other carbons. The secondary carbocation is more stable than the primary carbocation. And the reason that it's more stable is that the carbon atoms either side of the carbocation are able to push electron density towards the carbon. So the electrons in the bond between the 2 carbon atoms are attracted to the carbocation, and as the electrons travel towards that carbocation, you get a little bit of electron density around that positive charge, which reduces the magnitude of the charge and makes the ion more stable. If it's more stable, it's more likely to be formed. So when we form a secondary carbocation, we've got 2 carbons pushing electron density towards it. That's known as the inductive effect. And the inductive effect from 2 carbons will reduce the magnitude of the positive charge by more than in the primary carbocation, where the positive charge is on the number 1 carbon, and that carbon only has one other carbon attached, so therefore we've only got 1 carbon feeding electron density towards that positive charge, and so therefore the positive charge on the primary carbocation has not been stabilized as much as the carbocation on the secondary carbocation. So therefore 2-bromopropane is going to be our major product. And sometimes in exams you'd be asked to explain which of the products is formed in a higher concentration. And then finally we'll consider the electrophilic addition reaction between an alkene and concentrated sulfuric acid. Now in this case I'll go back to ethene as my alkene, and the ethene, if it reacts with concentrated if the ethene reacts with concentrated sulfuric acid, the sulfuric acid will not have dissociated, so the hydrogen will still be bonded to the oxygen. Because of the difference in electronegativity between the hydrogen and the oxygen, there will be a dipole moment, so the hydrogen will be slightly positive, the oxygen will be slightly negative, and therefore we will get an attraction between the electrons in the double bond and the hydrogen, so therefore we can form a bond between one of the carbons, it doesn't matter which one, and the hydrogen, and that will cause the electrons in the OH bond to move from being between the oxygen and hydrogen and will end up just on the oxygen, forming a lone pair. Again, we will form a carbocation intermediate, and that carbocation intermediate will be attracted very strongly to the oxide ion in the hydrogen sulfate ion, and so we'll get an attack coming from the lone pair of electrons making a bond with that carbon, and will form, as a product of this reaction, this molecule, which is called ethyl hydrogen sulfate. So the hydrogen sulfate is the functional group basically here, with an ethyl group C2H5 attached to the oxygen. Now that ethyl hydrogen sulfate, and this is the reason that this reaction is useful in industry, the ethyl hydrogen sulfate is able to react with water or steam and this will do a substitution reaction, a nucleophilic substitution. The lone pair on the water, on the oxygen on the water, will be attracted to the carbon delta plus, and we'll get a substitution reaction which will end up overall producing ethanol and the sulfuric acid again. And so therefore overall there is a reaction between ethene and steam in the presence of sulfuric acid, producing ethanol and more sulfuric acid. So therefore the sulfuric acid essentially behaves as a catalyst in this reaction. But the electrophilic addition mechanism for that process is as shown there. The nucleophilic addition elimination mechanism is a mechanism that only pops up at A level, and that's a mechanism with the acyl chlorides. Now the acyl chlorides react with 4 different nucleophiles, and the nucleophiles that we need to know about for this reaction are water, and so there's a lone pair of electrons on the oxygen and water, alcohols such as ethanol, where there is a lone pair of electrons on the oxygen, so both of these will react in a similar way with the nucleophilic attack coming from the oxygen, and then also two nucleophiles which use the lone pair of electrons on nitrogen, so we've got ammonia or primary amines, which we could have as NH2R, or in this case I'll go with methylamine, NH2CH3, again with the lone pair of electrons on the nitrogen. Now it doesn't matter which of these four nucleophiles we use, the mechanism works in exactly the same way. And so what I could do is I could represent any one of these nucleophiles as NuH, because all of these contain a hydrogen atom attached to the atom with the lone pair, which behaves as the nucleophile. And so the nucleophile there contains that lone pair of electrons. So as I show this mechanism, I'm going to first of all just show it using this generic HNU as a representation of any of these four nucleophiles. So if I take as an example, let's say propanoyl chloride, so we've got CH3, CH2, COCl, nucleophile is going to come in and attack. Now the nucleophile, because this is a trigonal planar orientation around that carbonyl, could attack from above or below the plane of these atoms. So what will happen though is it was most likely to come in from the opposite side to the C double bond O. So if I show our nucleophile here with that hydrogen, so we're going to attack the carbon, which will be slightly positive, which is why it's susceptible to nucleophilic attack. We'll form a bond between the nucleophile and the carbon, and that will cause the carbon-oxygen double bond to break. And so therefore we have done first of all a nucleophilic addition type reaction, and we produce as our product an ion which has both a positive and a negative charge. And what will happen next is two separate steps. We often draw it in one step. I'll show it as two separate steps to start with. So what will happen next is our elimination, and what will happen is that the carbon-oxygen double bond will be reformed, so that lone pair of electrons on the oxide ion will go back to between the carbon and the oxygen to produce a double bond, and the carbon-chlorine bond will break to eliminate the chloride ion. And so therefore we've done an elimination and will produce a chloride ion. Now this product here and the hydrogen, so the hydrogen can break off, can react with a base to remove that hydrogen. The pair of electrons will go from being between the nucleophile and the hydrogen onto the nucleophile to reform a lone pair of electrons, and will produce as our final product our new acyl compound plus H+. Now the H+ and the chloride can combine to produce HCl, but we don't show a chloride ion acting as a base to remove the hydrogen because chloride is not a strong base. So we've got two distinct steps here, or three distinct steps here. We've got first of all an addition reaction, the nucleophilic addition, where we break the double bond. Then we have the elimination step where we form a double bond, removing a small atom, or an ion in this case, from the molecule. And then the final step is this one, which is a deprotonation step where we remove the proton. Now, in an exam, it's perfectly acceptable to combine these two steps to just show three curly arrows in one step. And so it would look something like this. If we used as our example, let's go with propanoyl chloride again. And in this example, I will use the primary amine, so I'll use methylamine as an example. So we've got our methylamine, we've got our dipole, and we get the nucleophilic attack coming from the lone pair of electrons on the nitrogen to make a bond with the carbon, causing the carbon-oxygen double bond to break, so producing as our intermediate sorry, I do apologise, I've missed a hydrogen off that nitrogen. A positive charge there on the nitrogen, negative charge on the oxygen. So we then get our elimination. The chlorine atom breaks off to produce a chloride ion. The lone pair of electrons comes back to between the carbon and the oxygen to form the double bond, and one of these hydrogens will break off the nitrogen to form, or to remove, that positive charge. And so our final product will be the amide ion here, and that amide ion in this case would be called N-methyl, because that methyl group is attached to the nitrogen, so N-methyl propanamide. So N-methyl propanamide, and HCl will be the other product, which would appear as misty fumes as hydrogen chloride gas is produced. Obviously the products would vary depending on what the nucleophile was. So if the nucleophile is an amine, we produce as our product an amide plus HCl. However, if our nucleophile is water, we will produce a carboxylic acid. If the nucleophile is an alcohol, we will produce an ester. And then if the nucleophile was ammonia, we would just produce an amide rather than an N-substituted amide. In all of these cases, we would produce hydrogen chloride gas as another product. So the nucleophilic addition mechanism is one where a nucleophile, in this case either the hydride ion or a cyanide ion, for A level, not for IB, undergoes an addition reaction with aldehydes or ketones. Now, in addition reactions, a double bond will break and a species will add either side of the double bond in order to create a product without any double bonds in it. So two mechanisms we need to know here. The first one is where we have an aldehyde or ketone, any aldehyde or ketone, reacting with NaBH4. Now NaBH4 is a source of the H- ion, and the H- ion can be attracted to the carbon delta plus within the carbonyl. So if we take a carbonyl, let's take propanone. So the dipole moment over the carbonyl, the oxygen is slightly negative, the hydrogen is slightly positive because of the difference in electronegativity between oxygen and carbon, oxygen being more electronegative. And then the hydride ion from NaBH4 has a lone pair of electrons, and that lone pair will be attracted to the delta positive carbon atom, and so we'll form a bond between the H- and the carbon. Carbon can only form 4 bonds, so that will cause the double bond to break. And then the product of this reaction will be an oxide ion in the middle. The hydrogen will have attached to that carbon, and that will be our intermediate. Now, what will happen next is that oxide ion, the lone pair of electrons on that, will attack or will join with an H+ ion, so that could come from acid, or it could come from breaking water, so the oxide ion could attack the hydrogen delta plus in water, producing a hydroxide ion as another product, and we will have produced from our ketone a secondary alcohol, and so this is propan-2-ol. And so the product of this reaction is an alcohol from a ketone, and that is a reduction reaction. So as well as being a nucleophilic addition mechanism, the type of reaction here is reduction. Now, the other mechanism that we need to know at A level but not at IB is the nucleophilic addition reaction with cyanide. Now, if I take as an example here butanone, and react this with cyanide. Now, the cyanide ion has a lone pair of electrons on the carbon and a negative charge on the carbon, and that ion will be attracted to the carbon delta plus, so we will get an attack there, which causes the double bond to break. And we produce a nitrile with the O- as an intermediate, and then if we add dilute acid to this, we will attach the H+ to the oxide ion, and our final product will be a hydroxynitrile molecule. And so the name of this would be 2-hydroxy 2-methyl butane nitrile. So the nitrile, the CN becomes the main functional group in this class, in this homologous series, and so that will be your number 1 carbon. And then on the number 2 carbon there's a methyl group and a hydroxide group. Now, the reagents for this reaction would be potassium cyanide followed by dilute hydrochloric acid. The reason we use potassium cyanide and not HCN is that the potassium cyanide is ionic, whereas the HCN is a weak acid and only partially dissociated, so we wouldn't have a very high concentration of cyanide ions. The other thing that we can see in our product here is that the product will be optically active. It has a chiral carbon, the carbon there with 4 different groups attached, and so therefore optical isomers could exist. Now, doing this mechanism will produce a racemic mixture of the optical isomers of the 2 enantiomers, because the initial reactant here, the butanone, is trigonal planar around the carbonyl carbon, so therefore the nucleophile, the cyanide ion, is equally likely to attack from above the plane of the atoms or coming from behind, from below the plane of atoms, in order to produce our intermediate, and so therefore will produce a 50-50 mixture of the 2 enantiomers. Now, similarly to this, and this particularly comes up in IB, but not as a mechanism, but it's worth saying here that going back to our first reaction with the hydride ion, that if we had, instead of NaBH4 as our source of H- ions, if we have LiAlH4, then that's a stronger reducing agent, and that could react in a similar way with a carboxylic acid and end up producing an aldehyde, and then that could be further reduced to a primary alcohol. And so it'd be a similar reaction, but that's not one that you need to know the mechanism for. The electrophilic substitution mechanism, which takes place with molecules containing a benzene ring, so the arene class of molecules, of organic molecules, is a mechanism that comes up both at A level and at IB, but for IB there's only one of these. So I'll do the one that's common to both A level and IB first of all, and the reaction here is a nitration reaction, and it's a reaction between the benzene ring and the NO2 plus electrophile. So the NO2 plus is an electrophile that's produced by reacting concentrated nitric acid with concentrated sulfuric acid. Now, in this reaction, the concentrated nitric acid, which is HNO3, reacts with concentrated sulfuric acid to produce the H2NO3 plus ion plus HSO4 minus. Now, in this case, the sulfuric acid is behaving as a proton donor, and that, if you wanted to write that as a mechanism, would look something like this. So there's our HNO3. If we have an H plus, then we can form that intermediate, and then what will happen next is that that bond in the H2NO3 plus will break to form H2O and NO2 plus, with a positive charge there on the nitrogen. Now, you don't need to know that mechanism at A level. You might be familiar with it at IB, but what happens in the second part of this step is that another molecule of conc sulfuric acid will react with the H2NO3 plus ion, and in this case the sulfuric acid behaves as a dehydrating agent to produce the electrophile, the NO2 plus water plus the sulfuric acid. So the sulfuric acid actually is unchanged, although in the presence of water the sulfuric acid will lose a proton to form H3O plus and another HSO4 minus ion. And so sometimes if you're writing equations to show the formation of the electrophile, the NO2 plus, then you could write the full equation as being HNO3 plus 2H2SO4 produces NO2 plus H3O plus 2 HSO4 minuses. So now that we've produced our electrophile, we can then do the electrophilic substitution with our aromatic molecule, and in this case we will have an attack coming from the delocalized electrons around the benzene ring, forming a bond with the nitrogen, and that NO2 will now attach to one of the carbon atoms around the benzene ring. Now remember that round the benzene ring, each of these carbons in each corner is also bonded to a hydrogen, although the hydrogens are not shown in the skeletal formula. So I am going to show it now because it's important in the next step, and it's important to remember that this carbon here now has 4 bonds attached, and therefore this carbon cannot play any part in the delocalized ring system. However, all the other carbon atoms will have a p orbital which is able to overlap to form a delocalized system, so our ring now can go from this carbon round to this carbon, but no further. And when you draw this horseshoe, this broken ring, it's really important that the ring does not extend beyond the carbons either side of the carbon that the NO2 has attached to. Now, there is now a positive charge associated with the ring, and the positive charge would be on a carbon but can move around, which is why we draw it in the middle as if it was delocalized. Now, because we've broken the delocalized ring system, we have made an intermediate which is much less stable, and so in order to make the product more stable, the bond between the carbon and the hydrogen breaks, and the pair of electrons in that bond feeds back into the ring in order that this carbon atom can now become part of the delocalized ring again, restoring the stability associated with a benzene ring. And we produce as our product nitrobenzene plus H+. Now, in this intermediate, it's perfectly possible that the bond between the carbon and the nitrogen will break and those electrons go back into the ring and we go back to our reactant. And that will undoubtedly happen, and so therefore the reaction could be thought of as being a reversible reaction, and it's very unlikely that you will produce 100% yield of the nitrobenzene. Now, a use of that nitrobenzene is that we could then reduce it to produce phenylamine and to produce an aromatic amine. Now, that's not a mechanism that you need to know, but you do need to be aware that in the presence of a tin catalyst and concentrated hydrochloric acid, you could produce phenylamine. In fact, you'll produce with the acid the phenylammonium ion, which could then react with a base to remove the the extra hydrogen from the ammonium, from the nitrogen, and end up with phenylamine. And so this is an important mechanism in the production of aromatic amines. I'm not going to show the rest of the reaction there. The other reaction, the other electrophilic substitution mechanism that we need to know about at A level, but not at IB, is the so-called Friedel-Crafts acylation reaction. Now, this is where we react a benzene ring with an acyl chloride. So if I took as my example ethanoyl chloride, if we react that ethanoyl chloride with aluminium chloride, what can happen is that aluminium chloride, which is electron deficient, the aluminium only has 6 electrons around its outer energy level, can form a bond with the chlorine and to form AlCl4 minus, and leaving a positive charge on the acylium ion, and that positively charged ion there will behave as an electrophile. And so if we then react that electrophile with a benzene or an aromatic molecule, we'll get an attack like we did before, coming from the benzene ring, forming a bond between one of these carbons and the carbon with the positive charge. And so we'll produce as an intermediate this carbonyl compound. The hydrogen again was already attached to that carbon, and our broken ring again has to exist between this carbon and this carbon. It cannot extend beyond that with a positive charge, and then the carbon-hydrogen bond breaks. Both electrons now feed back into the ring to produce as our final product the re-established benzene ring, and we've removed H+. Now our product here is an aromatic ketone, and so this would be phenylethanone. It's unusual to have a ketone with 2 carbons in the main chain, but because we've got the phenyl group attached to the number 1 carbon, that's why it's a ketone as opposed to an aldehyde. Now the next thing that happens, the last thing that happens, is that the H+ product reacts with the AlCl4 minus that we produced initially, and this will produce hydrogen chloride gas, so we'll get misty fumes coming off from that, plus aluminium chloride AlCl3, which could go back to the start of the reaction and react with another acyl chloride, and therefore the aluminium chloride behaves as a catalyst in this reaction. But the mechanism here is the electrophilic substitution at this point here. Okay, so I hope you found this useful, this video useful. I hope it's helped you to understand in a little bit more detail the organic chemistry mechanisms. I suspect that this is perhaps a more useful video once you've been taught mechanisms in your own lessons, rather than a video to teach you everything from scratch. But again, if there are other videos that you think would be helpful, then please do leave a comment below, and do like, subscribe, share. Thank you for watching, and good luck with your studies in chemistry.